In this module, we're talking about the half-life of a first-order reaction using integrated rate laws, the integrated rate law for a first-order reaction. So what's the half-life? Okay, let's talk about that first. So this is the definition. It's how much time it takes for the amount, the concentration of a reactant to be cut in half. That's called the half-life. Now, so for this, and the symbol, by the way, is a T with the subscript 1/2. That's the half-life symbol. So for in a reaction that we've looked at before, the decomposition of dinitrogen pentoxide, if we look at the concentration versus time plot, it's not linear because it's first order, but if we suppose we start with a concentration of dinitrogen pentoxide initially of 0.1 moles per liter, half of that's 0.5. So the time it takes to get for the concentration to go from 0.1 to 0.05, would be the half-life. Notice that the half-life for a first-order reaction is constant. Okay? It's 100 seconds from here to here, and then the second half-life would be from 0.05 to 0.025 from here to here. That's also 100 seconds, and it keeps on going. So we can use the integrated rate law to get a useful expression for the half-life. So when the time is the time that's the half-life, that means that the concentration of the reactant is 1/2 the initial concentration. That's what we're saying here. So if we plug that in to a form of the integrated rate law that you've seen before, then the concentration of A is 1/2 the concentration of A0. Just replace A with 1/2 A0 in here. The A0s cancel, and the 2 comes up top. We get natural log of 2, which is just a constant. Now in your textbook, they put a number, they round that to 3 sig figs, which is fine, but we're just going to write natural log of 2 because you can always put that in your calculator. And that's just equal to KT, or solving. And now this time, though, this is the time when it's at the half-life, so it's T1/2. So solving for T1/2 divided by K. This is the expression for the half-life of a first-order reaction. Memorize that or derive it. So knowing the half-life, okay, we can find the rate constant, knowing the rate constant, we can find the half-life. We can play with this equation that I just showed you. For example, let's suppose we have a first-order reaction that's 38.9% complete in 49.7 seconds. Okay, we can find the rate constant and the half-life for this reaction. So we use the equation, solving for K. We're going to find the rate constant first. And rearrange it just like this. Make sure that makes sense to you guys. Now, okay, let's talk about this. If it's 38.9% complete, that means that 100 minus 38.9, or 61.1% of the initial reactant is still left. And so that means that if the concentration of A initially was 100, the concentration of A is going to be 61.1. So we just put 100 over 61.1. Make sure you do that subtraction there. And we know that the time it takes, 49.7 minutes. Take the natural log, divide, and we get the rate constant, 9.91 times 10 to the minus 3 per minute. There. And now that we know the rate constant, we can go back to the equation and find the half-life, just plugging in for K. Natural log of 2 over K is the half-life, and we get 69.9 minutes.